Hello, are you tired? Yes, I know. The previous topic was very long and multifaceted. For a change, today's part is very simple, easy, and enjoyable. Ladies and gentlemen, let me introduce the non-classical measures of dispersion. Finally, we move to the bottom of known scheme, in which we have non-classical measures of dispersion. Here we have absolute non-classical measures of dispersion. On the right side we have the relative non-classical measure, a singular, yes, non-classical relative measure of position, which is coefficient of quartile deviation. In group of non-classical measures of dispersion, we emphasize the quartile deviation and the group of measures called ranges, in which we have the range, interquartile range, interquintile range, and etc. First, we will talk about the absolute measures. At the beginning, we have the quartile deviation. This is an excellent substitute for the classical measures. This measure has a primitive construction because the only thing that we have to make is to make the computations of the difference between the third and the first quartile and divide this difference by 2. In other words, we can talk about the indicator of the average deviation of the first and the third quartiles from the median. As you can see here, we have the distance between the third quartile and the median. Here we have the distance between the first quartile and the median. So here we actually compute the average distance of the first and the third quartiles from the median. We denote the quartile deviation using the symbol of SQ. As I said before, this is an excellent substitute for the classical measures. Let's imagine the following example, in which we distinguish the following example of the individual series. The first expression 1, for example, the second value of our variable is 3, the third 6, and so on. And here we have 11, for example. This will be the first quartile of the variable values in this individual series. And 3 dots, maybe 44. This is the example of the third quartile, and so on. And at the end we have the last 3 values in the individual series. Let's take 56, 57, and 60. Okay, we are able to compute the quartile deviation, which is very easy. Quartile deviation, SQ here, it's a difference between the third and the first quartiles divided by 2. In our example, it's 44 minus 11 divided by 2, so it's 33 divided by 2, 16 and a half. Yeah? Okay. So we have indicated the dispersion in this example of the individual series very quickly. Okay, we can also compute here the classical measures of dispersion like mean absolute deviation and standard deviation. But first, we have to compute the deviations between the every value and the mean, yeah? And it depends on the measure. And after that, we raise these deviations to the power of 2. We compute squared deviations. Or if we talk about the mean absolute deviation, we compute the modules of these deviations. Yes, we sum up these squared deviations or modules of the deviations. Yes, divide them by the population size, compute the root, of the sum divided by n if we talk about the standard deviation, and finally we will receive the values of dx or sx. As you can see, it's not as fast as before, but obviously it is impossible to compute these measures. Alright, let's assume that the statisticians made some corrections here. The correction of the last value, which was 60, now it's 1 million. The question is, what will happen with the quartile deviation? The answer is absolutely nothing. Yeah, completely nothing. What will happen now with the classical measures of dispersion? Of course, they will rise significantly. Yeah. So the main conclusion is that quartile deviation is more resistant to the extreme values because it doesn't take into consideration, into an account, every value of the individual series. Yeah, here classical measures of dispersion are more prone to the extreme values, and we must stress that these values take into an account every value of our variable. Yeah, they take into consideration all the values of our variable. Here we take into consideration only 2 positional measures, and that's all. Yeah, here we have to compute every deviation, the deviation of every value, in which we have also the deviation of the extreme values. Summarized the problem, we should use non-classical measures of dispersion if we want to assess the degree of differentiation of the data set of the variable values. If we deal with the extreme values, if we don't have any extreme values, we can use, of course, the classical measures of dispersion. Okay, but here we don't see here, we don't see any changes of the differentiation if we change one of the extreme values. Yes, here we see the differences, yeah, before the change of the last value and after the change of the last value. So sometimes the advantage of the measure can be the disadvantage in the same time. All right, here we have the group of measures of dispersion called ranges. The first range is the simplest one. It's called simply range. This is the difference between the maximum and the minimum value. Two margin values: minimum value of our variable and maximum value of our variable. So this kind of measure indicates the scope, the range, the gap, yeah, between two extreme values, maximum and the minimum. Yes, so in the statistical series, if we talk about the ranges, the simply range is the biggest one. Yeah. The next measure is called Interpersonal Range. This is the difference between two margin percentiles, the 99th and the first percentile. So the range is higher or equal to interpercentile range. Yeah, here we have this difference. It can be indicated by the, here we have P99 and P1. This is difference between these two positional measures is called interpercentile range. Yeah, range is a different. It's the difference between the minimum and the maximum value, and of course, as I said before, range is greater or equal interpercentile range. The next range, as you can see here, we narrow down the ranges. The third form of range is Interdecide range. It's of course not greater than the interpercentile range. It's a difference between the last and the first deciles. Yeah, this is interdecile range. The next range is interquartile range. So the reasoning is the same. This is the difference between two margins quintiles, the fourth and the first quintiles. Difference between them, the gap between them, the range between them, the scope between them. And the most important measure is interquartile range. Interquartile range is not higher than the interquintile range. As you can see, we utilize this measure in the quartile deviation formula. Interquartile range, it's a difference between two margin quartiles, difference between the first and the difference between the third and the first quartile. Yeah. So if the differentiation of the variable values in the statistical series it's relatively small, so the difference between the ranges are also relatively small. If the differentiation in the statistical series are relatively high, so the difference between the ranges are also high. All right, let's move to the right side. Coefficient of quartile deviation. It's very simple measure. It takes the form of a relative measure. Yes, because there is no unit in the coefficient of quartile deviation, because if we consider the variable which is expressed, for example, in dollars, the difference between the quartile of between the third and the first quartiles is expressed in dollars as well, and median of the variable which is expressed in dollars will be expressed in dollars. Yes, so we can remove dollars from our measure and we express our measure in percents or in a decimal, and we show here the percentage. What percentage of the median is represented by the quartile deviation? Yeah, what percentage of the median is represented by a quartile deviation? So this kind of measure is very similar to the coefficient of variation of coefficient of mean deviation, but here the reference point is the median instead of arithmetic mean. We use here also the non-classical measure of dispersion instead of the classical ones like standard deviation and mean absolute deviation. And the properties, from that reason, the properties are analogous to the properties of coefficient of variation, and the properties of this measure are analogous to the properties of coefficient of variation and coefficient of mean deviation. Task 1. In some population interquartile range of the values of income, this is variable x, represents 42.6% of its median, and the values of weight, this is another variable, the weight, the values of weight are compiled in the table below here. So we have one population and two variables. First variable is income. Here we have the information about the differentiation of income, and here we have the information about the weight. Execute the following commands. First is to calculate and interpret range, interquartile range, and quartile deviation of weight of that. Okay, first of all, here we have cumulative relative frequencies. We need relative frequencies, of course. First relative frequency is the first cumulative relative frequency, 0.134. And the next relative frequency is the difference between the second cumulative relative frequency and the first cumulative relative frequency. So this is 0.211. The next one is the difference between 0.766 and 0.345. So this is 0.4 2, 1. And the last one is a difference between the last cumulative relative frequency. We know that the last cumulative relative frequency is equal to 1. So 1 minus 0.766 is 0.234. Yeah. And now we have the relative frequencies. Alright, so we are able to execute the first command. Please calculate and interpret the range and interquartile range. Range here is a difference between the maximum and the minimum value. The maximum value is the upper bound of the last class, 80, and minimum value is the lower bound of the first class, 41. So the difference between both values is 39 kilograms because the weight is expressed in kilograms. Yeah. So here the difference, the range, the difference between the maximum and minimum value is 39. Yeah. So here we have the first measure of differentiation. The scope of the values is 39 kilograms. Okay, let's compute interquartile range. We need two quartiles, the first quartile and the third quartile. First quartile is placed in that class in which cumulative relative frequency exceeds 25% for the first time. So it happens in the second class because this value is for the first time higher than 25%. The third quartile is placed in that class in which we exceed 75% for the first time. So it happens in the third class. So the first quartile is equal to lower bound of that class, 51, plus 0.25 minus cumulative relative frequency from the previous class, 0.134, divided by the relative frequency of that class, 0.211, and multiplied by the range of that class. And the final result is following: minus 0.14 divided by 0.211 multiplied by 9 and plus 51. The final result is 55.948 kilograms. So 25% of the population is characterized by the weight not higher than around 56 kilograms. All right. The third quartile of weight is 61. This is the lower bound of the third quartile class, plus 0.75 minus cumulative relative frequency from the previous class, 0.345, divided by 0.421, this is the relative frequency of that class, times 9. This is the difference between 70 and 61. Let's compute it. Minus 0.345 divided by 0.421 multiplied by 9 plus 61. And the final result is approximately 69.658 kilograms. So as we can perceive, we notice that 25% of the population, 25% of the population is characterized by the weight not lower, not less than 69.7 kilograms. Yeah? Okay, so here interquartile range is the difference between the third and the first quartiles. Here minus 55.948, 69.658 minus 55.948 is 13.71 kilograms. This is the difference, the scope, the distance between the third and the first quartiles. Yeah? It means that in the statistical series, here we have minimum value, here we have maximum value, here we have the first quartile, here we have the third quartile. So here the difference between the first and the third quartile is 13.71. The range is 39. Yes, so it means that we have some extreme, relatively extreme values. There is a high difference between these two measures of dispersion. Okay, so the interpretation is the distance between the third and the first quartile is about 13.71 kilograms. And the last is the quartile deviation of the weight. The quartile deviation of the weight is a half. Yes, it's a half of this distance between the third and the first quartiles. Third quartile minus first quartile divided by 2 is 13.71 divided by 2. It's exactly 6.855 kilograms. So the interpretation is the most important here, so we can write down average, the average distance between the first and the third quartiles of weight from the median is around 7 kilograms. Yeah, the average distance between the first and the third quartiles of weight from the median is around 7 kilograms. Okay, and the second command is to calculate and interpret the interdecile range of weight. In order to compute the interdecile range, we need two positional measures. The first decile and the last decile, the ninth decile. The first decile, D1, is placed in that class in which cumulative relative frequency exceeds 10% for the first time. Yeah, D1 is the x0 minus 0.1, 10% minus cumulative relative frequency of the previous class divided by f0 multiplied by, say, 0. Yeah, in our example we have the first decile is placed in the first class because here we exceed the 10% of the population for the first time. So first decile is equal to 41 plus 0.1 minus 0 because there is no cumulative relative frequency of the previous class. We don't have any previous classes, so it is equal to 0 divided by f0. F0 here is 0.134 multiplied by 9. Alright, let's take the calculator. 0.1 divided by 0.134 multiplied by 9 plus 41, and the final result is 47.716 kilograms. And then we can move to the ninth decile. Ninth decile is placed in that class in which we exceed with the cumulative relative frequency value the value of 90%. So it happens in the last class. So here we have 71 plus 0.9. Ninth decile means 9/10. Yeah? Minus the previous cumulative relative frequency from the -1 level, it's 0.766 divided by 0.234. This is the frequency of the ninth deciles class, multiplied by the range of that class. It's of course 9, so we can compute it. Yeah. It is around 76.153 or 155 actually kilograms. Yeah, 76.154 kilograms. Yeah, of course we know how to interpret that amounts, that measures. Yeah, please do it individually. And now we are able to compute the interdecile range. This is the difference between ninth and the first deciles. So we subtract 76.154 and 47.716, and this is 28.438 kilograms. So this is the interpretation is following the distance between the scope, the gap between the 9th and the first decile is about 28.4 kilograms. Yeah, we can summarize the problem. The difference between the maximum and minimum value was 39 kilograms. Yeah, the difference between the first decile, here we have x min, here we have x max, here we have d1 and d9, and q1 and q3, yeah, which represents the first and the 9th decile and the first and the third quartiles. Here the difference between the first and the last decile is 28.4 approximately, and difference between the third and the first quartiles was about 13, yeah, 13.71. 13.7 actually, yeah. So we have computed all ranges from the commands, yeah. Okay, we see a differentiation of the values of that variable, but we have to compare the differentiations between the weight, it's our variable here, and the incomes. Okay, so let's compute here the relative differentiation of the weight, the relative differentiation of the weight, and after that we will compare the relative differentiation of the weight expressed by the coefficient of quartile deviation with the coefficient of a quartile deviation of incomes. So our variable weight, we can denote this variable using y symbol, yi. So as you remember, quartile deviation of weight was 6.855 kilograms. We need also the reference point, the median of the weight. The median is placed in that class in which we exceed 50% of the population for the first time, so it is placed in the third class. Median here is 61 plus, yeah, because I'm talking about the third class, 61 plus 0.5 minus cumulative relative frequency from the previous class divided by 0.421 multiplied by 9. Yeah? Okay, so here the median is half minus 0.345 divided by 0.421 multiplied by 9 plus 61. Middle value is 64.314 kilograms. Yeah, so the half of the population is characterized by the value of the weight not greater than 64.3 kilograms. And now coefficient of quartile deviation computation is available. So it is VQ of y variable is SQ, the quartile deviation of y variable values, divided by median of y values. So we divide 6.855 by 64.314 kilograms, of course, but this coefficient has no unit. The final result is 64.314 is 0.107. Yeah, so this is about 10.7%. As we remember, the interpretation of this measure is following: average deviation of the first and the third quartiles from the median represents about 10.7% of the median. Yeah, so here we talk about relatively low differentiation of the values of weight. Yeah, it seemed to us that the difference between the ranges are high, but in the relative terms, the differentiation of the weight is actually relatively small. Yeah, so we had a wrong view about this phenomenon. The differentiation here is relatively small. Okay, and now let's compute the differentiation of the variable x values. We have the following information: interquartile range of the values of income represents 42.6% of its median. Yeah, so it means that interquartile range is equal to 0.426 multiplied by the median of the incomes. Yeah, this value represents 42.6% of the median of incomes. Yeah, so it means that interquartile range is equal to 0.426 of the median. Yeah, here we can denote the coefficient of quartile deviation using this version of the formula. It's interquartile range, the difference between the third and the first quartiles, yeah, multiplied by two medians. Let's check individually the formula, yeah, for coefficient of quartile deviation. And in our example, we have RQ of x is 0.426 multiplied by the median of x divided by 2 median of x. And as you can see, We don't need the information, yeah, because we can remove it from the coefficient, and the only thing we need is 2 times lower value. 0.26 divided by 2 is 0.213. So it's 21.3%. It means that the average deviation of the first and the third quartiles of incomes represent around 21% of their median. We can compare both values and we can prejudge that this population, which is characterized by the two variables, is more differentiated in point of view of incomes, yeah, because the module of VQX is higher than the module of VQY, yeah. The coefficient of quartile deviation for the incomes is higher than the coefficient of quartile deviation for the weight. Task 2. In some population, the first quartile of age is variable y, represents 65% of the median of age, and the third quartile of age is 1.5 times bigger than the median of age. And this is the end of the information regarding to the variable y. Here we have the information about the variable x, which is the housing spendings. The same population is characterized by the housing spendings, and below we can find inappropriate data about the housing spendings. So this situation is similar to the previous one. We have one population which is characterized by two variables: housing spendings and the age of the population. But the only difference now is that we operate by the frequencies instead of relative frequencies. And today, uniquely, here we have the frequencies expressed in thousands. It's okay, it's not a problem. And we have to compute and interpret quartile deviation and interquartile range of housing spendings. The first command is to compute the quartile deviation. As you know, we need two measures of position for the first and the third quartiles. Okay, in order to answer the next question in advance, we can compute also the median value. Yeah, it will be necessary in the next step. Let's start with the first quartile. Of course, before we compute the first quartile, we should determine in which class the first quartile is placed. We need to compute cumulate frequencies on the basis of this column. Yeah. So the first relative frequency, the first cumulative frequency is the same as the first frequency, 3.3, and the next cumulative frequency is a consequence of cross-adding 3.3 plus 4.04, and the result is of course 7.34. The next value of cumulative frequency is 7.34 plus 6.26, and the result is 13.6. The next one is 13.6 plus 3.9, and the result is 17.5, and the last one, the last number is the population size. Population size here is 20,000 people, yeah, 20,000 statistical units. All right. 25% of this population, 25% of this population is of course 5,000 statistical units. Yeah, 5,000. This is 25% of 20. It's 5,000. It means that we are looking for a cell in which we exceed 5,000 for the first time. We will receive the class of the first quartile. Here, no, here, yes. This is the place of the first quartile. The first quartile of housing spendings is somewhere between 1.6 and $2,000. Our variable x is expressed in dollars. All right. The lower bound of that class is 1.6 plus 25% multiplied by the population size 20 plus 1 minus the frequency, cumulative frequency of the previous class 3.3 divided by the frequency of that class 4.04 multiplied by the range of that class, which is 0.4. This is the difference between 2 and 1.6. Okay, we can compute that amount, that value. So 21 multiplied by 0.25 minus 3.3 divided by 404 multiplied by 0.4 plus 1.6, and the first quartile of housing spendings is $1.793 thousand. $1,000. So it means that 25% of the statistical units are characterized by the housing spendings not greater than $1.793 thousand. Okay. Now we are looking for the third quartile. 75% of 20,000 is of course 15,000. Yeah, so we are looking for the column in which cumulative frequency exceeds 15,000 for the first time. It happens in the fourth class. Yeah, we have here, going down, we have here the value which is higher than 15 for the first time. 2.6 plus 0.75, 20 plus 1 minus 13.6. This is the cumulative frequency from the previous class, divided by 3.9 multiplied by the range of that class, 0.4. Alright, and the final result, yes, I have a cheat sheet, which is 2.8 to $1,000. It means that 25% of this population, 25% of the population which is characterized by the highest values of housing spendings are characterized by the 25% of the statistical units are characterized by the housing spendings not lower than 2.8 to $1,000. Alright, and then we are able to compute a quartile deviation of the housing spendings, which is very primitive. Third quartile of housing spendings minus the first quartile of housing spendings divided by 2. This is an absolute measure, so it is expressed in the same unit as the considered variable housing spendings. So quartile deviation is expressed in dollars. 2.821 minus 1.793 divided by 2, and the final result is $0.514 thousand dollars. Yeah, so this is the average distance of the first and the third quartiles from the median. Yeah, about $1,500. Okay, and as I said before, median here is necessary if we think about the computation of coefficient of quartile deviation, and I have computed median earlier. You can check it at home. Median of housing spendings is $2.302 thousand. Check it out. All right, we are able now to compute the interquintile range of housing spendings. Interquintile range is the difference between the last and the first quintile. Yeah. So we are looking for the classes of fourth and the first quintile. All right, we need some more space. We are dealing with first quintile. First quintile means 1/5 of the population. The population size is 20. 20% of the population is 20 by 5, 4,000 statistical units. Yeah, so Therefore, we are looking for the class in which we exceed 4,000 for the first time. It happens in the second class. This is the class of the first quintile. And we also need the information about 80% of the population. 80% of the population is, of course, 16,000. We exceed 16,000 for the first time in the same classes as earlier. All right. And now we can compute both measures. The first quintile is 1.6 plus 1/5 population size plus 1 minus cumulative frequency from the previous class divided by 404 multiplied by 0.4. Yeah, and the final result is $1.689 thousand. And the fourth quintile is 2.6 plus 4/5, 20 plus 1 minus 13.6. Yeah, this is our 0 level, this is the -1 level. 3.9 multiplied by 0.4, and the final result is $2.928 thousand. So the interquartile range is the difference between both values. It is 1.233. Oh, maybe we can use a calculator. Yeah, it's a good idea. 928 minus 1.689. The difference is 1.239. Yeah. So here we have the value of interquartile range. It means that the distance between the third and the first quartiles is $1.239 thousand. Okay, and the last comment answer the question: is that population more varied in point of view of age or housing spendings? Here, on the basis of this information, we can compute coefficient of quartile deviation of housing spendings. So we divide quartile deviation by the median, the quartile deviation of housing spendings by the median of housing spendings, 0.514 divided by 2.302, and we receive the relative measure. Which is equal to 0.223. Yeah, so here we are talking about a moderate variability of housing spendings values, because quartile deviation is about 22% of the median of housing spendings. So the variability is moderate. Okay, and now finally we can utilize the information from the first sentence in the task content. In some population, in this population, the first quartile of age represents 65% of the median of age. It means that first quartile of age, variable y, is 65% of the median of age. And the third quartile of age is 1.5 times bigger than the median of age. Yeah? Alright. Let's utilize this information. Coefficient of quartile deviation for y variable is third quartile minus first quartile of y variable, of course, divided by 2 medians. Okay, so it means that 1.5 medians minus 0.65 median divided by 2, the same medians. Yeah? Alright. 1.5 minus 0.65 is 0.85 medians of age divided by 2 medians of age. Medians of age play no role here, so we can remove them from our computations, and the final result is 0.85 divided by 2, so it is 0.425. Yeah, this is relative differentiation. Yeah, this is the value of coefficient of quartile deviation, a relative measure. So we can compare these differentiations. Yeah, and we can say that this population is more differentiated in point of view of age. Yeah, so the statistical units are more similar to each other in respect of housing spendings, and at the same time the statistical units are more different from each other in respect of the values of age. Yeah, and that's all. Actually, here we can write down the final conclusion. As you already know, the information about the differentiation of one variable may appear in the task content. Like here, in some population, first quartile is 30% of the median, and the third quartile is blah blah blah. Yes, this is the information about the differentiation of the variables values. Here, this example is solved here. We can move to the next example, in which we have, in some population, median represents actually 1/3 of the interquartile range. Please give me the coefficient of quartile deviation. The coefficient of quartile deviation is the interquartile range divided by two medians. And we know that the median represents 33.3333 and so on. It means 1/3 of the interquartile range. So we can put here the value of median interquartile range divided by 2, and the median is 1/3 multiplied by RQ. Yeah, we can remove the RQ from the fraction, and we have what? 1 divided by 2/3. It means that coefficient of quartal deviation is equal to 1.5. It means that it is equal to 150%. Here we are talking about the extreme high variability of the values of considered variable. All right, and that's all. Thank you very much.